In this talk, we delve into the EPR experiment, its connection to quantum entanglement, and Bell's theorem, a journey into the heart of quantum mechanics that challenges our understanding of reality, causality, and locality. We begin with the celebrated EPR experiment, as reimagined by Bohm and Bell. Consider a neutral pion particle decaying into an electron and a positron via the process shown in equation 3.45. The principle of conservation of momentum ensures that the electron and positron fly in opposite directions, and conservation of angular momentum requires the system's total spin to be zero. The state of the system is therefore a maximally entangled spin state, known as the Bell state, given in equation 3.46. This state signifies perfect quantum entanglement. If the electron's spin is measured by Alice to be up, the positron's spin must be measured by Bob to be down, and vice versa, each with equal probability of 1/2. This is the hallmark of quantum entanglement. In essence, the measurement of Alice collapses the state vector and leaves no room for maneuver for Bob, whose measurement will be necessarily anticorrelated. The Hilbert space of this system is the tensor product of the two-dimensional Hilbert spaces associated with the electron and positron. The tensor product of two fundamental representations of the unitary group SU2 associated with the spins of the electron and positron gives the direct sum of two irreducible Hilbert spaces associated with spin 0, defining the singlet state, and spin 1, defining the triplet states, respectively, as shown in equation 3.48. By conservation laws, the system of electron and positron must exist in the singlet state defined in equation 3.53. This entangled state ensures that the measurement of one particle's spin immediately determines the other's, even if they are separated by vast distances, what Einstein famously referred to as spooky action at a distance. Now, consider the scenario where Alice, on one side of the universe, measures the spin of the electron along an arbitrary direction hat A, while Bob, on the opposite side, measures the positron's spin along direction hat B. Quantum mechanics predicts the expectation value of the product of these spin measurements to be proportional to minus the scalar product of the two unit vectors hat A and hat B, as shown in equation 3.56. This precise prediction is a cornerstone of quantum mechanics and highlights its inherently more than probabilistic nature. Einstein, along with many proponents of local realism, argued that the properties of particles exist independently of measurement. In their view, the observed probabilities in quantum mechanics are a consequence of incomplete knowledge, requiring the introduction of hidden variables. These hidden variables, coupled with the wave function, would deterministically predict the outcome of any measurement. Bell formalized this notion into what is now known as Bell's inequality, which any local hidden variable theory must satisfy. For three measurement directions, hat A, hat B, and hat C, the inequality reads as in equation 3.60. Here, P of A and B represents the expectation value of the product of the two spin measurements when the directions are hat A and hat B. The main hypotheses underlying this inequality are classical realism, also known as local realism, which states that properties of system exist before measurement, and local causality, which states that no physical action can propagate faster than the speed of light. Bell's theorem shows that these extremely reasonable assumptions are not compatible. It states precisely that no physical theory based on local hidden variables can reproduce all the predictions of quantum mechanics. The proof of Bell's inequality is a very simple argument shown in equation 3.61. Quantum mechanics fundamentally violates Bell's inequality. For example, when hat A and hat B are perpendicular, and hat C makes a 45 degrees angle with both, quantum mechanics prediction yield the expectation values shown in equation 3.62, which clearly fails to satisfy Bell's inequality. This result is not just a theoretical quirk. Experiments like those conducted by Aspect in the 1980s have confirmed that nature aligns with quantum predictions, not with the constraints of local hidden variable theories. As a consequence, Bohr's Copenhagen interpretation, which is still the majority view, states that the state of the system actually does not exist before measurement, which is what seems to be indicated by Aspect's experiment. To underscore the significance of this violation, consider a simple analogy from classical set theory. Let A, B, and C represent three properties with corresponding sets. Classical logic dictates that the number of elements in set A but not B, plus those in B but no C, must be greater than or equal to the number in A but no C. This is given in equation 3.63, which is Bell's inequality in this context. The astonishing statement of Bell's theorem is that quantum mechanics violates this very logical intuition. In summary, the EPR experiment, Bell's theorem, and the violations of Bell's inequality challenge our deepest assumptions about the nature of reality, locality, and causality. They reveal a quantum world that defies classical logic and operates in ways that remain deeply mysterious and profoundly fascinating.